So our presenter today is Joe Xivier. He received his bachelor in technical degree in electrical and electronics engineering from Mahatma Gandhi University in India with distinction. In 1993, he started his career as a protection engineer. He joined ABB India in 1996 and served over 13 years before moving to ABB in the United States. During this year, Joe has been involved with application and marketing of protection automation, medium voltage, high voltage products and system of ABB. Currently, Joe is the West Region Technical Manager for ABB Distribution Protection and Automation Division based out of Camas, Washington, and he is involved with application, marketing, training and solution building for customer in utilities, industries, transportation and infrastructure segments. Joe has authored several technical papers on protection and automation applications, and he is an active member of IEEE PES Power System Reliability Committee as well. Thank you, Joe.
All right. Thank you, Nina. And welcome again for those who have dialed in to today's discussion on generator protection fundamentals. Good morning from the West Coast of the United States. I guess in other parts of the US, it's PM. So anyway, wherever you are tuned in from, we are glad that you have joined us today. And for today's discussions, this is what we will go through. Power generation fundamentals, and then briefly take a look at the generator faults and abnormal conditions which is faced by generators. And then we will have a discussion on the typical generator protections and time permits. We will look at some of the application examples. Generator protection is a very vast subject with several protections. So 1 hour is a very short period of time to cover entire protection in great detail. So we will definitely look at some of the important ones in detail and mention the lesser important ones as we go through the different slides. So let's take a look at the typical arrangement in a power plant. So in a power plant, obviously the important piece of equipment is the generator. And we have the generator. Generators can vary in different sizes, all the way from small generators to medium-sized generators, large generators, and very large generators. So in a typical power plant, this is the arrangement. Generators driven by a prime mover, which is a turbine or a diesel engine, depending on the case. And the turbine is driven by mechanical energy, either from steam or it's from other sources. And then for a synchronous generator, there's a DC excitation which is required to produce the power by the generator. So we have a separate circuit for the excitation system with its own circuit breaker called as a field circuit breaker, and there is an excitation transformer which actually feeds the power to the excitation system. And there could be a generator breaker. There may or may not be a generator breaker, but typically there will be one. And then we have a step-up transformer. So generators typically generate voltage in the medium voltage range, and it is stepped up by a step-up transformer, normally called as a generator step-up transformer, GSU, and then it is connected to the bus bar of the substation where it gets transmitted out. And there also is an auxiliary transformer to feed the auxiliaries of the power plant. And so this is the typical arrangement. And of course, the generator is grounded. We will look at the grounding system in the upcoming slides. So these are the different power plant layouts. here, or the one at the left here is a similar one which we saw in the previous slide. So there can be cases where there is no generator breaker. So there is no dedicated generator breaker where the generator is directly connected to the step-up transformer, and then there will be a unit breaker here. So this is called as a unit transformer, and this is a unit breaker, and it is grounded. When there are multiple generators, this could be the arrangement, the multiple generators having its own individual circuit breaker, generator circuit breaker, which are in turn connected to the common bus bar. From there, the voltage is stepped up and then connected to the high voltage grid. And the other arrangement could be by using a multi-winding step-up transformer. So this step-up transformer is having two low voltage windings, each winding having a generator connected to it. Okay, so these are some of the common methods. And on the grounding side, there are different ways of grounding the transformer. These are some of the common ones. The one on the left is a resistive grounding, which is typically a low impedance grounding, where a resistor is connected in between the generator neutral and the ground. So this is the resistor which limits the ground fault current. So which means lower the resistance value, more the damage to the generator winding during an internal fault. So if it's a low impedance grounding, the fault current can be typically in the range of 200 to 400 amperes. And then the other method is high impedance grounding. So high impedance grounding uses a single phase distribution transformer connected between the generator neutral and the ground. And with a ground fault current, in this case, it's typically less than or equal to 10 amperes. So as you can see here, there's a resistor connected to the secondary side of the single phase transformer, and the value, the resistor is selected so that a single phase to ground fault at the generator terminals, the power dissipated in the resistor is equal to or greater than 3 times the total zero sequence capacitance or capacitive kVA to ground. So that's a basis on which the value of resistance is selected. Typically, it's about 0.5 ohms. There is another method of high resistance grounding, is using a secondary tunable reactor to limit the maximum ground fault current. The ohmic value of the secondary reactor, if it's used, is selected such that when reflected to the primary circuit, its reactance is equal to 1/3 of the total zero sequence capacitive reactance. This type of grounding limits the single phase to ground fault current to less than to 1 ampere or even lesser. So that's the benefit of that type of grounding. And the third one is having a grounding transformer at the terminal side. So here you can see that the grounding transformer is connected to the terminal side so this transformer is a Y delta connected transformer with the neutral point of the transformer is directly grounded, and the secondary side of this transformer is connected in broken delta with the resistor across to it. The value of this resistor is in terms of ohms, which with a typical value of about 3 ohms. The secondary winding voltage typically is about 500 volts. And the other method is with no intentional grounding of the generator stator winding. So you can see there is no physical connection here. The only grounding path is the natural capacitance of the generator stator winding. And there are some problems with this kind of arrangement with the small winding capacitances, ferroresonance, and high transient over voltages in case of ground fault. So practically, all connected generators are high impedance grounded generators. So here you can see a plot to indicate the type of damage or the severity of the damage which can occur to stator in case of a ground fault. So if the current is limited to less than 15 amperes, we can see the extent of damage is pretty small compared to large fault current. So if you can see here, from if the currents, the fault current or the ground fault current is less than 50 amperes, it's less than 15 amperes, negligible burning. Slightly above that, slight burning, and if it is above 50, there could be severe damage to the generator. So the grounding of a generator is very important. Now let's take a look at the different type of faults which can occur in a generator. So these are some of the common faults: the stator short circuit, stator ground faults, rotor ground faults, stator and rotor interturn faults, then external to the generator unit transformer faults, then other external faults. So there are also faults which can occur due to the operations or operation related faults, like overcurrent or overloading, unbalanced, over temperature, under and over voltage, under and over excitation, under and over frequency, over fluxing, asynchronous running of the machine, out of step or pole slip, then generator motoring condition, failures in the mechanical control system, like automatic voltage regulator or governor failure. There could be failures in the machine cooling system, and failures in the primary equipment itself, like the breaker, or an open phase condition. So it's important that we protect the generator and the system against all these different types of faults. So now looking at the different protections which are important for a generator. As we know that generator has three parts which work together. The one is the stator, the rotor, and the turbine. So the protection functions are allocated to different parts of these of the generator. Like, for example, the stator has these protections allocated to it, like differential over voltage and so on. And then the rotor has these different types of protection allocated to it. So these protections are primarily to protect the rotor, and then for the turbine, it is reverse power and under and over frequency. So in olden days, when during the electromechanical protection days, even they're still used in many parts of the world, there were individual relays for each of these different functions. So you can imagine that generator protection system comprises of 2-3 different panels of all these different type of relays mounted and wired onto it. But with the modern microprocessor relays, all these different protections are built into one single device, which is pretty nice and compact. So now let's look at the different types of protection in a little more detail. The first one is the stator short circuit protection. Face-to-face short circuits in a generator are relatively rare, but when such faults occur, the consequences are severe. When the short circuit occurs, the insulation is damaged. During the fault sequence, the local heating caused by the fault current will further damage the insulation. And in addition, the windings in the stator core will get damaged. So short circuits in the generator will cause large fault currents. And these fault currents will result in large forces that will create mechanical stress to other components in the power plant. There are risks of fire and explosion in connection to the short circuits in the generator, as there are inflammable material in and close to the generator. And the short circuit itself will result in torsion variations causing mechanical stress on generator and turbine shafts. So short circuit can cause both electrical and mechanical problems in the generator. So the speed requirement on fault clearance is pretty critical for a short circuit fault because the short circuit causes a very large current, and so it should be cleared as fast as possible. In a short circuit condition, the fault current is fed from the external network where the generator is connected to, and from the generator itself, because generator is producing power in itself. The short circuit current from the external network, which is often the largest part to the total short circuit current, is interrupted by tripping the generator and or the unit breaker. The short circuit current fed from the generator itself is handled by tripping the field circuit breaker and by interrupting primary power to the turbine, like closing of the valves, etc. This contribution to the total short circuit current cannot be instantaneously cleared, even if the protection is very fast. That means the internal contribution cannot be instantaneously cleared. So how do we detect stator short circuits? There are a number of different kinds of protections capable to detect and initiate trip in the case of a stator short circuit. The one important and the foremost is the generator or an unit differential protection. This is commonly used for all generators, typically about 2 megawatt size of generator. And the directional negative sequence overcurrent protection can operate as a fast protection for unsymmetrical short circuits in the generator. In this case, the protection fed from the CT and the PT on the generator terminal side has direction towards the generator. So it looks into the generator and provides a fast clearance time. The other types of protection can serve as a redundant protection and also as a protection for faults in the external network. So, like for example, the under impedance protection or overcurrent protection are important for detection and fault clearance of external faults fed from the generator. So what is the feature of a generator differential protection? Like all other differential current protection schemes, generator differential protection is also absolutely selective. This means that only faults within the protection zone. The protection zone means the zone between the current transformer. I have a scheme coming up in the next slide. So there are two sets of current transformers required to achieve the differential protection. So the fault within the zone is to be selected or to be acted upon by this differential protection. Faults in the connected network are not detected. The generator differential protection can thus not be used as a backup protection for external faults. So it's a unit protection. Differential protection will trip instantaneously for all internal faults, as there is no need for delay to achieve selectivity. Also, the generator differential protection will be able to detect fault currents much smaller than the generator current at normal operation, giving good sensitivity. As I mentioned, the current transformers are required on both sides of the generator windings. And the generator differential must be designed so that the current transformer saturation and external fault does not give unwanted trip. So that is one of the important things to be dealt with by protection engineers how to avoid a false trip or a misoperation in the event of a CT saturation condition. So here is how the scheme operates, the differential protection. We have two sets of CTs, one set on the terminal side and the other one in the neutral side, and these CTs are connected to the protection relay. So for an internal fault, the differential current will be the vectorial sum of the neutral side generator current and the terminal side generator current. And there is a bias current or the restraint current. It will be the largest phase current on the neutral side at the and the terminal side. So as you can see, in the event of a internal fault, the differential current is going to be much higher, and the ratio between the differential current and the bias current is larger than 1, and which makes the differential protection to operate. So this will happen only in the event of an internal fault. Whereas in the case of an external fault, so here the fault is outside the protection zone. The protection zone is defined by this area where the CTs are located, and here the fault is outside of this protected zone. The differential current is 0. At the same time, we will have a bias current equal to the phase current. So which means the protection will have a good stability, which means that it will be stable against external faults. Differential protection scheme should operate only for internal faults. So we need to deal with some of the inherent problems in the electrical system when we design the differential protection scheme. One is to dealing with the DC constraint, and there is a possibility of enhancing the stability for DC constraint, which should with a DC constraint setting, which decreases the sensitivity temporarily to avoid trip on external faults. And there's a possibility of CT saturation based blocking, preventing unnecessary tripping due to magnetizing inrush current. So when you have a inrush current situation, that could be a CT saturation. And when it comes to large generators, we can make the differential protection more sensitive by using negative sequence unrestrained differential protection principle. In this case, a negative sequence current based internal or external fault discriminator is used. It enhances the bias differential protection to increase speed and security. The negative sequence current standalone fault discriminator gives a very sensitive generator protection. This option can be blocked for large currents though. So what does a generator differential protection do? If a differential protection picks up, it is due to an internal fault in the generator. This means that the plant must be shut down as fast as possible, and no attempt for house load operation shall be made. And we need to trip the turbine control system, which will control the active power from the turbine to the generator. It will be reduced as fast as possible, and other different actions are made depending on the type of the power plant. Then we need to trip the field breaker. This is important in order to reduce the fault current from the generator itself. The trip signal to the generator breaker, this is important in order to reduce the fault current from the external network. In many power plants, there is no generator breaker, only a unit breaker at the high voltage side of the unit transformer. So to trip of the unit breaker in the case of a generator breaker does not exist. If the generator breaker exists, the unit breaker should not be tripped, as there should be a possibility to maintain the connection to the auxiliary system via the auxiliary transformer connected between the generator breaker and the unit transformer. So here is a scheme. There are different differential protection schemes possible. One for 87G for the generator itself, the other for the 87T, which is for the unit transformer, the step-up transformer, and then 87O, it's an overall 87 overall differential protection, which looks at the current comprising. So this overall as a protection zone comprising both generator and the transformer. Now let's take a look at the differential protection characteristic. In the electromechanical relays, we had only the possibility of a single slope characteristic, but with the modern microprocessor relays, we have the possibility of creating multi-slope characteristic. And how is it beneficial? So here you have the multi-slope characteristic, which has 3 sections here, and the bottom portion of it is a non-trip area, and here is a trip area which is a conditional trip, and above this limit is the unconditional or unrestrained operation of the protection. And here we have, this is the plot between the operate current, which is a differential current, and the restrained current or the bias current. So the section 1 is the most sensitive part of the characteristic. In section 1, normal currents flow through the protected circuit and its current transformers, and risk for higher false differential currents is low. So with generators, the only cause of a small false differential current can be the tolerances of the current transformers. There could be CT ratio mismatch and so on. So the slope in section 1 is always 0%. So it's a flat curve. Normally, with the protected machine at the rated load, the restrained bias current will be around 1 per unit, that is equal to the machine rated current. Whereas in section 2, a minor slope is introduced, which is supposed to cope with the false differential currents proportional to higher than normal currents through the current transformers. And when we move to the slope 3, we have a much higher slope, and it is designed to result in a higher tolerance to substantial current transformer saturation at high through fall currents, which may be expected in this section. So having a multi-slope characteristic, which it helps into the stability of the protection. Again, the typical settings here for this characteristic. Section 1, the operation level, the normal setting is within the range of 10 to 20%. And this is a place where there is no much of CT saturation. If we consider a maximum current error in opposite direction of the CTs on each side of the generator, this can result in a false differential current as shown in the figure, about 10% of the generator current. In section 1, there is no risk of CT saturation. In section 2, large currents can be suspected as minor CT saturation can occur. All right, so, and in section 3, there is large risk of CT saturation for external faults. So this moving this slope upwards will help combat that situation. So here's a look at a picture for CT saturation. If the CT on one side of the generator saturates while the CT on the other side is unaffected, there will be a significant false differential current. Okay, so as you can see here, this is a current from the CT neutral point and the current from the generator terminal side, and this CT is going through saturation, which will cause this false differential current to be seen by the relay. For short intervals, there is a risk that the differential current enters the trip area, so we need to handle the situation. And also the DC biasing. In the case of a fault with a very long DC time constant, there is a risk of saturation of a CT feeding the generator differential protection. To minimize the risk of unwanted trip due to this DC current saturation, there is a possibility to have a DC current depending bias contribution with a slow decay, or desensitizing the protection temporarily in such situation. So you can see from here the CT is saturated because of the DC constant. Then we have the under impedance protection. The under impedance protection has two different tasks: detection and fault clearance of internal faults in case the main protection, that is the differential protection, fails. And the second task is to detect and clear the fault of an external fault, mainly in the case where the main bus bar or the line protection fails. In some power plants, there is no bus bar protection on the high voltage side of the unit transformer. In such cases, the under impedance protection is the main short circuit protection for bus faults. So you can see here, the under impedance functions are taking the current CT and the VT input here, and then acts as a backup. So in a typical impedance trajectory, so this is what happens. This is a plot between the resistance and the reactance plane, the impedance plane. In a typical impedance trajectory during a short circuit, the fault impedance remains inside the impedance circle for a long time, in which case the under impedance protection provides longer tripping delay times to maintain the time selectivity. As we mentioned, this is a backup protection. So the protection scheme is looking for the locus of the impedance here. In very large systems, under impedance with multiple zones are helpful. For example, in this case, the zone 1 is used for generator and transformer backup, and zone 2 is used to back up external faults. So there could be multiple zones in the under impedance element. And then we have the phase over current protection, which again has two different tasks. The primary one is to detect and clear faults, internal faults in case of a main protection failure, which is a differential protection. And the second one is to detect and clear external faults, mainly in case of a main bus bar or line protection failure. Then we have the generator short circuit current. It actually has to do with the impedance of the generator or the generator reactance. So during a short circuit sequence, the fault current from the generator will change, and this is due to two phenomena. The impedance of the generator will increase during the fault sequence. During the first moments, the generator impedance is equal to the sub-transient reactance, which is typically 15 to 25% of the reactance. The impedance will gradually increase to the transient reactance, which is in the range of 25 to 35%, and to the stationary reactance. So that there's a change which happens in the event of a fault. the fall current from the generator is also dependent on the internal voltage source, that is the excitation of the generator. The excitation system is made in different ways for different power plants. So the short circuit current also depends, is primarily depending on the generator reactance, and it varies. So the next one, the protection consideration is voltage controlled overcurrent protection. And why voltage control overcurrent protection? Because in the event of a fall, the terminal voltage drops or changes, and we can achieve, this is typically used for a system with a direct connected generator. In the case of a short circuit, the sustained fall current of the generator can fall well below the full load current. Okay, so a regular overcurrent may not operate in this situation. The sustained fall current is determined by the generator's synchronous reactance, as we discussed earlier, and the effective pickup value is calculated based on the equation here. We can achieve two characteristics here. One is called as a step characteristic. This is achieved with the settings of the element with a voltage high limit equal to the voltage low limit. And then we can achieve also a slope characteristic when the voltage high limit and low limit are different. So this will be the operating, the operating value will depend on this slope which we set, and it depends on the voltage of the generator as well. So the pickup value of the overcurrent pickup value varies according to the availability of voltage. So in the case of an external short circuit, the generator overcurrent protection serves as a backup protection. If a normal overcurrent protection is used, as I mentioned, there is a risk that the current will be reduced to a value less than the set trip level before the set time delay has elapsed, and the protection will thus not give a required trip in that case. So with the voltage dependent overcurrent function, the trip can be guaranteed. Okay, you can see that in this curve here. Now we move on to the stator ground fault protection. The stator ground fault will result in current flow into the stator core, and as the stator core's main core is made laminated with insulation between the layers, the ground fault current will influence the insulation between the layers and enable induced additional current flow in the stator. The consequence will be that the stator iron core will be destroyed and needs to be replaced. So if the ground fault is situated close to the generator terminal, the voltage in the healthy phases will be increased. This gives an increased risk of a second ground fault in another phase. The fault currents caused by the stator ground fault is small as a consequence of the high impedance grounding system. Therefore, a relatively long fault clearance time can be accepted. So here is where the ground fault measurement is done by measuring the residual voltage from a voltage transformer connected between the generator neutral point and the ground, and the voltage, the residual voltage, is equivalent to the open delta connected phase voltage transformers. Here, one possible disadvantage by using the neutral point voltage transformer is the voltage transformer can have a winding interruption undetected, as the neutral point voltage is normally zero. So this is how we measured that. So as I mentioned, the current, the other way of detecting a stator ground fault is by measuring the neutral current. The current measurement is in the neutral point is equal to the neutral point voltage measurement, as we can see here. So, excuse me, the CT, the neutral CT will measure the ground fault current, and we can make it work. So this is typically called as a 95% stator ground fault protection, and we will see in the upcoming slide why it is 95%. There is another method which is called as a 3I0 current measurement, where the 3I0 value is measured by the residually connected CTs. And one difficulty with the solution is that the current transformer ratio is normally so large that the secondary residual current will be very small. The fault residual current due to difference between the three-phase current transformers can be in the same range as the secondary earth fault current. Okay, so that's one possible disadvantage with this scheme. So here is a look at what happens. The 95% stator ground fault typically measures the fundamental frequency voltage component in the generator start point, and it operates when it exceeds the preset value. By using this principle, ground fault protection for approximately 95% of the stator winding can be protected. So, which means the last 5%, which is closer to the neutral of the generator, remains unprotected. However, detecting a ground fault close to the generator neutral is very critical or crucial for a large machine. So maybe up to medium-sized machines, the last 5% can remain, but it is always good to have 100% stator ground fault protection. By using the normal methods, we can protect only up to 95% of the winding. So we need to have additional protection to cover the last 5% of the winding. Sorry. There are possibly two methods to do that. As I mentioned, it is critical to detect and clear a stator ground fault close to the generator neutral. However, this is impossible to do with a simple residual overcurrent or residual voltage ground fault protection only. And because of that, we have this method of 100% stator ground fault protection. The generator will not generate a pure sinusoidal wave, as stator windings are not perfectly shaped to give this perfect voltage. The generator will give a certain degree of harmonics in the power generator. The third harmonic voltage generated has the characteristics of a zero sequence voltage. This means that there will be a third harmonic voltage in the generator neutral during normal operation. In case of a ground fault close to the neutral, this third harmonic voltage will be reduced and can therefore be an indication of a fault. If the third harmonic voltage is very small, another principle for 100% stator ground fault protection can be used, which is a non-harmonic voltage injection in the neutral point of the generator. If this injected voltage gives a corresponding current, this is an indication of a stator ground fault. Okay, so the simplest approach is third harmonic under voltage in the neutral and third harmonic over voltage at the generator terminals. The possible problem with this approach is that this protection may not be effective during generator startup and generator shutdown or different generator loading conditions. because, as I mentioned, the third harmonic will be fully be available only when the generator is in its full load condition. Okay, so we have to the more effective way of sensing or providing 100% protection is a third harmonic differential principle, where we have a differential voltage calculated between the third harmonic content from the neutral side and the terminal side. And then, of course, it has a bias characteristic where with the magnitude of the third harmonic bias voltage. So here is how third harmonic content looks like in the different operating situation. In the normal operation, you have you have so much third harmonic, which is equal in from both sides of the generator. When there is a fault at the neutral, then the third harmonic content reduces or falls in the neutral side. And when there's a fault at the terminal, it happens the other way. So this is a good way to detect 100% or the last 5% or protect the last 5% of the stator winding. Okay, here is another look at the connection. So we have the fault here, the fault resistance, and then we derive the third harmonic voltage from the neutral side and the terminal side. So the neutral point fundamental frequency over voltage protection provides protection for up to 90% of the winding, and the rest of the 10% is provided by this third harmonic principle, and we achieve 100% protection for the stator against ground fault. Okay, then there is a rotor ground fault protection. The field circuit of the generator is normally isolated from the ground, and so with a single ground fault in the rotor circuit, it is still possible to run the machine without generator damage. However, if a second ground fault occurs, then it could lead to severe damages, and it could be a face-to-face fault situation in that case. So there is the requirement of a fast clearance system is moderate in such a situation. In large generators, injection principle is adopted for rotor ground fault protection. Now, before we move on to the other protection, which I will navigate through pretty quickly, you need to understand the different operation conditions. The synchronous machine operating in parallel with a large power system can supply active power to the system. Then it operates as a generator. If it receives active power from the system, it operates as a motor. It supplies reactive power to the system in an overexcited machine. Then it acts as operates as a shunt capacitor. If it receives reactive power from the system, it's an underexcited situation. And it may be noted that the machine will have fixed rotating speed at all these times. Okay. So the rest of the protections are based on these different planes. There are 3 different planes considered for protection. Operation, one is the UI plane, or the VI plane is generally used for generators rated with power factor 0.8 or 0.95, depending on the machine design. PQ plane is used to determine generator capability curve, and the RX impedance plane is used for deriving loss of excitation, pole slip, under impedance protections. Okay, so as you can see, depending on the exciting situation or excitation situation, the machine can act as a generator and a motor. Okay, so loss of excitation, it could be due to an open field circuit or a field short circuit, accidental tripping, or loss of field at the main exciter. So the consequence of such situation is that the machine speed can go higher than the synchronous speed. It can cause asynchronous running and stator and core heating, and it also can induce rotor currents. Okay, so that needs to be protected as well. So in a loss of excitation condition, the apparent power loci moves in this fashion during in that situation. So we can see that the apparent power takes a path like this. Okay. The operation characteristics is typically an offset Mohr circle in the impedance plane, okay, for loss of excitation detection. And this circle is parameterized with the offset, diameter, and the displacement setting values. So you can see here A is a impedance locus in under excitation condition for heavily loaded machine, and this is the impedance locus in under excitation condition for lightly loaded machine. Whereas C is a impedance locus for fault in the network. So if the impedance locus enters this relay operation characteristic, which is an offset Mohr, then we call it a fault, and then a fault situation, and the relay is called to trip. Then there is another condition called a generator motoring, which is the other way when the machine is underexcited, which can be due to mechanical failure or mechanical power problem from the prime mover, and then the generator will act as a synchronous motor and starts importing power from the system. It is not a dangerous operating condition for the machine itself, but it may be dangerous for the prime mover. So the extent of damage in such a situation will depend on the type of the prime mover. So we need to take care of that situation as well. It can cause, as we said, the causes due to loss of prime mover, low water flow in the case of hydro systems, load variations, etc. And the effect can be overheating of turbine and turbine blades, and it can cause cavitation of blades in the case of hydro units. So this protection demands accurate active power measurement. So this is a method we use to detect such situation. 32R, which is a reverse power, and 32O is a reverse directional over protection. 32O, or the directional over power protection, protects against excessive power flow in the set operating direction. And 32R is intended for the prime mover, such as diesel engines or turbines. Okay, then there is an under power protection. This protects the generator from very low power output conditions. There is so this is a characteristic for that. Steam turbines can become easily overheated if the steam flow becomes too low or ceases to flow through the turbine. And with the parallel connected generators, disconnecting the low load generator and allowing the remaining generators to feed the network is more economical. So we need to detect a generator which is delivering under power, and then should be able to isolate that from the system. Then there is a negative sequence overcurrent protection. negative sequence current is caused by unbalanced loads. It could be due to non-transposed transmission circuits, unbalanced system faults, series faults, or circuit breaker pole discrepancy, or open circuits. The negative sequence current flow through the stator winding, inducing negative sequence voltage in the rotor winding. So this can result in a high rotor current that damages the rotor winding. The frequency of this induced current is approximately twice the supply frequency. And due to skin effect, the induced current with a frequency double the supply frequency encounters high rotor resistance, which leads to excessive heating, even with phase currents with value less than the rated current of the motor. So the negative sequence impedance of the induction or a synchronous machine is approximately equal to the lock rotor impedance, which is approximately 1/6 of the normal machine impedance. Okay, so with a negative sequence current, there could be severe damages. The rotor gets heated up, and there could be severe damages to the machine. So we need to provide adequate protection for against a negative sequence. Okay, because as we see, the heating of the machine is proportional to the square of the current, right? So that becomes more critical. Then we have the out of step or pole slip protection. It detects the loss of synchronism or out of step condition between the generator and the rest of the power system. The reason for out of step condition could be power system faults, sudden large change in load conditions, or problem in field excitation system causing under excitation. Okay, the protection must be able to distinguish between the stable and unstable power swings, which is important because there could be power swings in the system, and we should be able to detect which is unstable and which is stable. So for that purpose, we use a characteristic like this. This protection uses two impedance measurement elements known as the inner and the outer blinders, as you can see here, on Moe characteristics with the timers. The Moe characteristics is divided into two zones. So here you can see the power swing situation. In A is a situation where there's a power swing, but the system is stable. So we don't need to, in a power swing situation, the locus will not enter in the operating zone of the protection. And B is a situation where there's a power slip where the impedance locus enters the operating region and then moves out. Okay, and C is an impedance locus where there is a fault situation, so which goes and stays inside here. So we can detect the pole slip or out of step condition based on this locus of the impedance. Then we have the frequency protection. 81 over frequency protects in case of turbine over speed, and under frequency comes into play to protect the steam turbine at the critical speed situation. It is important to have a frequency adaptivity during generator startup condition and also during shutdown phases, because during those situations there is a low frequency and low voltage condition exists, which is a normal thing, which is not because of a fault. So in case of an internal failure in such condition, the fault current can be even lower than the nominal current. Okay, and also the internal failure must be detected before the generator is connected into the network. That is very critical because we don't want a faulty generator to go into the system, which can cause more serious damages. So the frequency adaptivity enables sensitive and selective protection during generator startup and shutdown phases. So here the operating range is typically from 12 to 90 hertz at 60 hertz. Okay. Then we have the over voltage protection 59. Over voltage condition will occur in the power system during abnormal conditions such as sudden power loss, tap changer regulating failures, open line ends, and on long lines. This function can also be used for open conductor detection or switching on off of the reactors and capacitors when combined with the directional reactive power function. Then we have the thermal overload protection. This is again very crucial for a machine protection standpoint. The heating of a machine depends on time constants here, and it is an exponential curve, as we can see here, the heating characteristics of a machine, and this is due to the fact that the temperature is proportional to the square of the current. Okay, so it is not a flat characteristic, it takes a characteristic like this. Okay, and we don't want the heating to exceed the allowable or the maximum temperature withstand capability of the machine. And there is a bearing insulation protection. This is to protect the bearing insulation, or you know, in order to avoid excessive heating of the bearing. So if we don't take care of this, there could be bearing damages and stator and rotor damage. And so this is how we can do. One of the ways is to measure the current here at the shaft here. And alternatively, RTDs are used to measure the rise in temperature, and it can be integrated with the protection device to trip the generator. Okay, there are ABB provides several solutions for generator protection from Reliant family, which is called as REG. As you can see, G stands for protection, and there are different devices available and can be chosen depending on the size of the machine. REG 615 from small to medium-sized generators, and REG 650 and 670 for large to very large machines. I know that it's been quick in some of the protection elements, but maybe I'll take a couple of minutes more to just run through some of the applications examples. For example, REG 615, it's a very compact design with a draw design here. It provides protection, control, measurement, and supervision of small to medium-sized generators used in diesel, gas, hydroelectric, combined heat and power, and steam power plants. So it comes in two different configurations, configuration C and D, as we can see here. And it also comes with the 100% stator at fault protection. This is an application example with several generators connected in parallel, where the ground fault is typically restricted to 3 to 5 amperes. This is an example of a medium-sized generator protection, where we can use two different modules, two variants, configuration D and configuration C. One taking care of the differential, other one taking care of the 100% stator ground fault protection. This is another example, protecting a generator block connected or unit connected transformer. We have one relay for taking care of the generator protection here, and the other one taking care of the overall protection of the transformer, and including the transformers. Okay, so in conclusion, a generator is a very valuable piece of equipment in the power plant, and it needs to be adequately protected so that we can have a stable, uninterrupted, I'm sorry, it's not uninterrupted. We need to interrupt the generation if there is a genuine fault in the system. With that, I will take any questions you have.
Thank you, Joe, for presenting today's topic, generator fundamental protections. I'm going to switch quickly the screen so everybody can see the questions. Can you see my screen now, Joe?
Yes, I can.
Perfect. So the first question that we received today is, why is there a boosting CT on the generator apart from the differential CTs?
I guess I did not get the boosting CT part, but if you're, let me answer this question the way I understand it. The differential CTs are dedicated CTs, so you cannot have additional any other protection devices connected to that CT. So for a differential protection element, we need to have these dedicated CTs on both sides of the generator. Now, if in the older schemes with the electromechanical relays or the solid state relays, as I mentioned, there are different protection devices used for different protection elements. So in such cases, there are additional CTs used to feed or derive a current for additional protection. For example, under impedance or voltage control overcurrent protection. But if you will see that with the modern microprocessor relays, we don't need separate CTs, because the same set of CTs will act as a feeding point for all the multiple protection, including differential protection, and that is segregated internal to the device. Let me see whether I can go back up.
If you need to present your screen, let me know so you can be the presenter again.
Oh, okay. I was trying to show the one of the schemes here.
Okay, let me give you control.
Yeah.
There you go.
Yeah, thank you. So, so you can see here that we have two sets of CT only in this case, right? You have the neutral side CT and the terminal side CT, and this is the CT input which is used for all different type of protection. So we don't need a separate CT in addition to these differential protection CTs. This is a ground fault detection transformer here, which is used for detecting the ground faults. But other than that, there are no other CTs required in the modern protection relays. So I hope I have answered that question. But if you have still more, just you can always send us an email to understand your situation better, and then we can definitely discuss on that. Back to you, Nina.
Our second question is, why is this data protection referred to under impedance instead of overcurrent?
That's a good question. Stator protection, as I mentioned, is primarily protected by differential protection, right? So if the other protections like under impedance and overcurrent are acting as a backup for that in case of a differential protection does not operate or fails. So in the overcurrent protection, as I mentioned, in the event of a fault, the terminal voltage of the generator falls or dips, and it may not provide enough current. The overcurrent or the current generated might not be adequate enough for regular overcurrent protection to operate. So one of the ways to detect such situation is using a voltage control over current, as we discussed. And under impedance protection is also a backup protection where we look at the impedance loci movement, and if in the event of an under impedance protection, the impedance locus stays inside the operating area long enough so that we can make the protection to operate. And eventually it moves out of the the operating zone of the relay, but we'll have some time for the protection element to pick up and operate, which is not the case in a normal overcurrent protection.
So the same attendee asked also, can you explain on a practical level what the difference is between the restraint and operation current is? I'm not sure if you mentioned this in your answer.
No, that's again a great question. So the operation current and the restraint current are used to determine the characteristic of the differential element. So if you remember the multi-slope characteristic, which I've shown towards the beginning, it is a plot between the operation characteristic, which is the differential current. The differential current is derived between the differential current of the terminal and the neutral side of the CTs, and then a bias current or a restraint current is derived in order to provide more stability to the protection element. So it's basically a balancing act. So if you want in crude terms, operating current will try to operate the element. The restraining current is connected or is connected in such a way. I'm talking now in terms of electromechanical relays. It will oppose the operation of the relay. So both act in opposition. So in the event of an internal fault within the protected zone, the differential current or the operation current will be high enough to make the operation over the restraint. The restraint current will be lower and the operation current will be higher in the event of internal fault, and the relay will eventually operate. Whereas in the case of a external fault, the restraint current will be higher than the internal or the operation current or the differential current. So that's how the system is stabilized in the event of an external fault. So that is the practical side of it. And this is derived inside the relay. So we are not feeding different CTs for it. This is derived based on the current from the both sides of the generator. Next question.
(10p) class, to what ANSI class it corresponds?
Great question again. The 10p IEC class is, that's IEC nomenclature. The ANSI, again, I would say it is, I don't have an exact number. It could be the ANSI standard goes with the C200, C500. So type of CTs. So that could be the CT which could be chosen, and we have calculation examples for it depending on the machine size, which probably we can share with you.
T is the time constant for a short circuit at generator terminals. How can we estimate the time duration for a short circuit on the high side of the step-up transformer?
I will have to go back to the slide.
Okay.
Let me go there. Just give me a second. I don't know where you picked from which slide you picked that question from, but if we, can you show that question again, Nina?
Sure. Give me 1 second, please.
Yeah. Okay, so if I understood your question correctly, the time constant tau is design characteristics of the generator. Okay, so estimating the time duration of a short circuit on the high side of the step-up transformer, the time constant I mentioned, I referred with respect to the thermal protection. But if we are thinking of a short circuit protection on the transformer side, we can achieve that by the differential protection. As I mentioned, we can have a differential protection dedicated for the transformer, and then for large systems there's an overall differential protection. So it is not dependent on the time constant. It depends again by the measurement of the current from both sides of the protected zone, and in the event of a differential current that element operates. So we don't need to be looking at the time constant for stator short circuit protection. Hope that answers. Next question, Nina.
Before reading this question, I will apologize with the participants because we're taking over time. I appreciate your time. I think we will try to answer all the questions until 3:30. So after 9 minutes, if we don't answer the questions, we will answer them by email or send the question and answer directly to you in the follow-up email that you're going to receive tomorrow. So thank you very much for your time, and we're going to continue until 3:30. So why is under impedance protection called under impedance when there is a short circuit occurs, and how is the impedance affected? Is it because when there is a short circuit, the current increases and the voltage decreases?
Yes, that is exactly right. And the impedance of the machine is affected or varies based on the situation. So, which means if you remember the impedance plane, we have the RX curve plot, and there is a impedance characteristic for the machine, and the relay operation is defined by the impedance settings. Now, in the event of a short circuit, the impedance locus moves, which is generally external to the more characteristic which you have seen, and then it enters into the more characteristic of the relay. So that is the locus or the movement of the impedance in the event of a short circuit. So which obviously says that impedance decreases as in the event of a short circuit. So the impedance falls into the operating characteristics of the relay, which will be sensed by the relay and then makes a determination to operate. And and again, there is another phenomena here, is that the terminal voltage of the transform or the generator might fall because of the fault, but again, there will be a feeding from the external circuit because it's connected to the grid, and there's a contribution from internal of the generator as well. So there are two contributions which are coming here. So in any case, the impedance locus moves into the operating characteristics of the relay, and then it determines to operate. With that, I would, since we're out of time, are we taking more questions, Nina?
It depends on you if you want to keep going. I just need like 2 minutes to close the webinar, so maybe you can ask 2 questions more.
Okay. All right.
So what is the effect of load, like linear or non-linear, on generators?
It does have effect on the linear and the non-linear loads. Most of the majority of the loads are, again, it depends on the type of the power plant configuration and the generator connection point where it is connected. In the if it's a power plant, for example, hydro power plant, which is remotely in a remote location and gets connected to the grid, the effect is not as much. But if it is a industrial generator, for example, which is connected within the facility into the system, then the generator sees the nonlinear loads much closely than in the other case. So it definitely it does not have the I don't know what exactly meant by the effect of load. Loading of a generator, if it creates an unbalanced situation. So unbalanced loading of the generator is not good, and because as we saw, the unbalance of loads can create negative sequence currents, which is not good for the machine. So if it is a balanced load situation, it won't affect generator as much.
If we have to replace one differential CT after 20 years, do we have to replace it in pair?
Great question. Excellent question. So the requirement, I would put it this way: the requirement for a differential protection to operate accurately is that the CTs should feed the same current, right? So if it is always recommended to get the differential CTs from the same vendor with the same turns ratio, which means if you are replacing, it does not mean that you can get an accurate CT after 20 years, but one has to make a careful study of what is the existing CT on one side and the characteristic of the CTs which you're buying after 20 years. And in all probability, the CT saturation characteristic and the ratio and all, if it is different, it can cause misoperations or nuisance operations. But there are several mitigation techniques available or settings possible in the modern microprocessor relays. But in any case, we need to make sure that both side CTs have the same characteristics. That is very, very important.
So last questions for today. At external faults, CT saturation can give unwanted trips. In such cases, can sensor technology be used in generator protection systems?
Absolutely. Sensor technology is the best way to go, if you ask, because the sensors are not affected by the saturation. That is one the benefit of having a sensor, which is sensor has two advantages. One is it is not affected, or it is not having multi ratios. It has just one big range for current measurement. The other benefit is of a sensor is that it won't have saturation issues. So having a NCIT or a non-conventional instrument transformer is the best method to go. But if we are applying it to in an existing situation, then we may not have that. But sensor technology will help in avoiding CT saturation issues.
Thank you, Joe. Those are all the questions for today. I would like to take 1 minute to let you know about our training sources, which is basically our next webinar, a practical guide of troubleshooting IC 61850 goods communication, and it's going to be presented on September 13 at 2 p.m. In the PDF of this presentation that you can download from Handout, you can click on this register link to obviously to register for the webinar. And here in this slide, you can find all the webinars that we have presented so far this year. So the ones in color red are the ones that are coming, and the ones on green, on gray are the ones that we already presented. So you can access both through the links on each square. Also, and finally, we have our contact information for Joe Xivier. You can find his email if you need to ask him any technical or commercial question about the topic presented today, or if you have question about training program or collateral, you can send me an email. Thank you very much to everybody for the time. We know that we took 15 minutes additional, and we appreciate your time. Thank you, Joe.
Thank you, Nina. Thank you, everyone, for joining today.